Remember how the structural portion of the tower acts as a reinforced concrete beam, checked earlier, and a column? Now we will check it as a column under an eccentric axial loading, which I show here in the diagram. Overall, it is not normal to see horizontal and vertical forces acting simultaneously on a reinforced concrete column. So what we'll do to check them is use a biaxial bending diagram. The final product should look like this, where we explore the capacity limits of the column and then plot our actual load experience or the demand to make sure it's within these limits. And I'll post this picture below so that you can read through the diagram and check out which loads will govern at which points, and it's helpful for understanding the biaxial loading on the column. Overall, x-axis is moment, which is both the moment caused by the eccentric axial load, in our case, the moment caused by the eccentric axial load, and the moment caused by horizontal cable forces. The y-axis is axial load from the vertical cable forces. We'll plot the nominal and then the factored load capacity for a single tower column in order to form the range in which our demand must fall. Before we dive into these calculations for the toward-away river plane, we need to rule out the out-of-plane eccentric axial load, so we don't need to use a three-dimensional biaxial loading diagram. To recap, the toward-away river moment is what combines with the cable forces and is our main concern, which is shown here. The moment caused by the eccentric axial load that is deemed out of plane or along the river will be ignored. This is from section R22.4.2.1 of ACI 318. The normalized eccentricity is close enough such that we don't need to consider flexural effects. Effective column depth is 40 centimeters, and the out-of-plane eccentricity is 5 centimeters. 5 over 40 is 0.125. If we consider masonry, 5 over 70 is 0.07. So this puts us within the limit described for a tied column, which is less than 0.1. Because of this, we're going to neglect it. Now moving on to the creation of the interaction diagram seen above, I like to set my spreadsheet up term by term. We'll go through the main body of the diagram, then special conditions and limits to round it out. And remember, concrete has zero capacity and tension, only in compression, assumed here. And that's from design assumption number 4, section 10.2.5 in ACI 318. So the reinforcing steel picks up the full tension load and some of the compressive load. In our case, the section will look like this, with reinforcing bar at the top and bottom. We have section dimensions H and B with depth to the top and bottom rebar as well as clear cover. We'll take and all of these dimensions can be found on the tower details. We'll take the reinforcing bar to be 16 millimeter bar and the tie bar to be 10 millimeter. The strain diagram shows the top and bottom steel strains, concrete compressive strain, and C, which is the distance to the eccentric axial load. The force diagram shows A, which is the depth of the concrete compressive section, as well as the steel tension or compression and the concrete compression. To create the body of the diagram, we will vary C from 0 to 30 centimeters. This will help us find the main portion. And later, we'll back calculate C for the 4 strain conditions and the maximum and minimum conditions. A is the depth of the concrete compressive block, which we take to be 85% of C from the code. The need for this 0.85 shape factor, beta, is due to the variation in shape of the stress strain curve for different concrete strengths. We'll use this 0.85 because that is what is shown in the code in figure 6-10. ES1 is the bottom steel strain, taken as C minus D1 over C times ECU. This is outlined in design assumption number 1 in the code, section 10.2.2. D1 is from above the depth of the bottom steel, which is just that, that height minus clear cover minus the diameter of the tie bar minus the diameter of the bar divided by 2. So D1 is that distance to the center of the bottom bar. ECU is the design maximum for concrete compressive strain, explained in design assumption number 2 in section 10.2.3. And that's always taken as 0.003 meters. Negative strain indicates tension, which makes sense here, that ES1 will always be negative for C up to 30 centimeters if we're measuring from the top of this section here, because the full depth is 70 centimeters and the load will never pass that half point, that midway point. ES2 is the same as ES1, except we'll use D2, which is the depth to the top steel, taken as the clear cover plus the diameter of the tie bar plus the diameter of the bar over 2. Now, things get a little more complicated. FS1 is the bottom steel stress, which depends on the strain. If ES1 is greater than the yield stress of steel, 40 KSI, over the elastic modulus of steel, 29,000 KSI, which is the maximum strain or the yield strain, we will take it as the limit stress of 40. If it is less, we will take it as ES1 multiplied by the elastic modulus, or whatever the calculated strain is, or stress is at that, under that strain condition. FS2 is the top steel stress and is similar. If ES2 is greater than max strain, we'll take it as the limit stress. If it is less, we will take it as the calculated stress. But because the top steel can go both into tension and compression, we need to make sure to add a limit in the both positive and negative direction. This follows design assumption number 3 in section 10.2.4, which sets up these equations for the calculation. Next, we'll calculate the forces in the concrete and steel pieces. So first, CC is the compression in the concrete. Remember that it is assumed no tension is picked up by the concrete. This is calculated by the equation 0.85 times FC, which is the compressive strength of concrete, times A times B, or the concrete compressive strength multiplied by the dimensions of the concrete compression block. Another 0.85. Remember that another 0.85 is multiplied into the equation to account for the concrete displaced by steel in compression. This comes from design assumption number 6, section 10.2.7. We now have 2 sets of reinforcing bar to calculate forces. The bottom bar will always be in tension in our range of C values, and the top bar will vary from tension to compression. We'll calculate the tension or compression in these bars with this equation, AS times number of bars over 2 times FS2. In this case, AS is the area of steel, the total area of steel reinforcing bar. This equation also comes from design assumption number 6, 10.2.7. So to reiterate, it's the area of the steel multiplied by the ratio of the number of bars in the bottom or top, or the total number of bars divided by 2, because there's an equal amount on the bottom and top, multiplied by the stress in those bars. And if you do a dimensional analysis, you'll see how this just gives a force. So finally, we can calculate our axial and moment capacities. First, the nominal axial capacity is just going to be the sum of the concrete compression and steel tension and compression. This comes from section 10.3.6, for the maximum axial strength. Remember that signs are important here. We'll take the factored axial capacity as 0.65 multiplied by the nominal. And because this is the most conservative value. This is a conservative assumption, and the load capacity reduction factor will be the first thing we examine if we need to sharpen the pencil and this calculation does not pass, because this 0.65 can and should probably go up to 0.9. To find our moment capacity, we'll take each loading, remember from the diagram above, CC, TS2 or CS2, and TS1, and multiply it by its lever arm. And that gives us the equation here that comes from 10.3.1. Note that the sign will switch for TS2 if it is in compression. I won't go through this equation explicitly, but you can refer to the diagram above in the lecture notes to figure out how these actual geometric calculations are being made with the h/2 and a/2. So that concludes the calculations for the main body of our interaction diagram. Personally, I like to use an Excel spreadsheet here to calculate one full row of numbers, then drag to vary C from 0 to 30 centimeters and get a full suite of values. In the following sections, we'll discuss the special cases and the maximum and minimum values to help create the nice shape of that interaction diagram. I know this is a lot of information, so please refer to the lecture notes and the text below. Go to the references in the code, take a moment to digest this before we go into the next section. It will take a little while to set this up as a spreadsheet, and remember, once again, that signs are really important if you're getting strange numbers.